From now on, we're going to go through a list of criteria to decide convergence or divergence of a numerical series. And the first one of these is called the integral test. In some way, we've already talked about the integral test or implicitly used it when we discussed the converse of the nth term test in the previous module. Remember that we pointed out that if the sequence of general term doesn't go to 0, then the series is divergent, and we pointed out that the converse is false, giving as an example the series, the harmonic series, a series from n equal 1 to infinity of 1 over n, and we justified that this series is divergent even though the sequence of general term 1 over n goes to 0, using an argument that is based on comparing the series or the partial sums with the integral of the function 1 over x. Just to remind you what we did, we looked at the partial sequence of partial sums, Sn, so sum from 1 to 1 over n, 1 plus 1 half plus 1 third up to 1 over n, and try to represent this partial sum geometrically and compare it with the area under the graph of the function 1 over x. Specifically, what we did is point out that 1 can be represented as the area of the square that has one side on the x-axis on the interval from 1 to 2, and whose height is given by the value of the function 1 over x on the left-hand point, which in this case is a value at 1, so is 1, and therefore this square has area 1. 1 half, on the other end, could be represented as the area of the rectangle that has one side along the x-axis on the interval 2, 3, and whose height is given by the value of the function 1 over x at the left-hand point, that is at 2, and that height is 1 half, so the area is 1 half times 1, 1 half, and then we can keep doing that. 1/3 would be represented by this rectangle, where the height is given by the value of the function at the left-hand point, in other words, value at 3, which is 1/3, and so on. And we keep going until we represent, say, 1 over n. And you see that this sum of the areas of these red rectangles is an area that is greater than the area under the graph of the function from x equal 1 to x equal n plus 1, right? N plus 1 because, well, as you can see here, if for instance we were looking at just the first three terms, so 1, 1 half, and 1/3, then the corresponding part of the x-axis that we're considering is from 1 to 4. So we have that the partial sum, Sn, is greater or equal to the integral from 1 to n plus 1 of 1 over x, which we can calculate to be natural log of n plus 1. And because the natural log of n plus 1 goes to infinity when n goes to infinity, so does the sequence of partial sums. And this is a way to justify that the series of 1 over n is divergent. Now let's try to apply a similar reasoning to a different series, a series from 1 to infinity of 1 over n squared. So again, the sequence of terms 1 over n squared goes to 0, but we have seen that it's not enough to conclude that the series is convergent. So let's try to see whether we can say something about the convergence of this series following the same line of thought that we have applied to series of 1 over n. So we look at the graph of 1 over x squared and try to represent the terms of the partial sum Sn, 1 plus 1/4 plus 1/9 and so on up to 1 over n squared. So for 1 I can represent it as the area of the square that has one side along the x-axis from 0 to 1 and whose height is given by the value of the function 1 over x squared at the right-hand point. So this is at 1 and I get 1, therefore the area of this rectangle is 1. And for 1/4 I can represent that as the area of the rectangle that has one side along the x-axis on the interval from 1 to 2 and whose height is given by the value of the function at the right-hand point, that is at 2. The value of 1 over x squared at 2 is 1/4, so I have one side of length 1, the other one of length 1/4, the area is 1/4. And then similarly, 1/9 corresponds to the area of the rectangle with one side along the x-axis on the interval from 2 to 3, and the height given by the value at 3, that is at the right hand point of the interval, which is 1/9. And we keep doing that until we get to 1 over n squared. And you see that we get this red area that we could compare not exactly to the integral of the function from 1 to n, but something similar, because this area, this blue area here, is the area under the graph of the function on the interval from 1 to n. And therefore, it is the integral of 1 over x squared from 1 to n. That means that the red area is less than or equal 1, which is the area of the first square that we left out, plus the integral from 1 to n of 1 over x squared. But we can calculate this integral, namely it is an antiderivative is negative 1 over x that we evaluate between 1 and n. So we get negative 1 over n plus 1. Adding the 1 from the red square, we obtain 2 minus 1 over n. That means that Sn, the sequence of partial sums, Sn, is bounded above by 2. And moreover, it's an increasing sequence, because you see that Sn is a sum of positive terms. And if I go from Sn to Sn plus 1, I just take Sn and add another positive term, so I get something greater. So what I have for the sequence of partial sums, I have an increasing sequence bounded above, so it is convergent. And therefore the series is convergent, because the series by definition is just a limit of the sequence of partial sum. And moreover, we know that this limit is at most 2, therefore we can conclude that our series is convergent, and as a extra piece of information, we know that the sum is no more than 2. So now we can generalize this line of reasoning to the situation where we look at the series from 1 to infinity of terms of the form f of n, where f is a continuous, positive or non-negative decreasing function on the interval from 1 to infinity. So something that looks like that. And let's try to go through the steps of this reasoning again. So here I can represent f of 1 because I'm looking at the rectangle that has as a base one of the sides is along the x-axis on the interval from 0 to 1, and the height of that rectangle is simply the value of the function f at 1, that is at the right end of the interval. So we get a rectangle that has one side of size 1, the other one of size f of 1, so the area is f of 1. Then I can look at the rectangle that is built the same way. I take an interval of length 1 on the x-axis, so we are from 1 to 2, and then I evaluate the function at 2 at the right hand point of the interval. I get height f of 2, so the area of the rectangle is f of 2. And we can keep going that way until we get a rectangle of area f of n, and the sum of the areas of these red rectangles is f of 1 plus f of 2 and so on plus f of n, and therefore is the nth partial sum for our series. We can compare it with the integral of the function, which exists because the function is continuous positive on the interval 1 infinity. Namely, this blue area here is the area under the graph of the function f over the interval from 1 to n, and therefore is the integral from 1 to n of the function f. And the red area, which corresponds to our nth partial sum, is less than or equal to the first rectangle, which corresponds to f of 1, plus the blue area, which is the integral from 1 to n of f of x dx. So that's enough to conclude that if the integral, the improper integral from 1 to infinity of f of x dx is convergent, then the series is convergent as well, because then the sequence of partial sum Sn is an increasing sequence. That's because we're adding positive terms, and it is bounded above by a finite number, and therefore it's going to be convergent. However, we would like to have the converse. In other words, if the improper integral from 1 to infinity of f of x dx is not convergent, in other words, is divergent, then we would like to be able to conclude that the series is divergent as well. And indeed, this is the case. All we have to do is shift our rectangles, and you see that in that way we can compare our n's partial sum not with the integral from 1 to n, but with the integral from 1 to n plus 1, because we've shifted our rectangles by 1 unit to the right. And now this blue area is less than the sum of the areas of the rectangle. In other words, what we have is that the integral from 1 to n plus 1 of the function is less than or equal to the n's partial sum. But now that means that if the integral from 1 to infinity of f is divergent, then s of n has to be divergent, because we get s of n is greater or equal to something going to infinity when n goes to infinity. So we obtain that our series is convergent if and only if the improper integral from 1 to infinity of the function f is convergent. In other words, that means if the integral is convergent, so is the series. If the integral is divergent, so is the series. So that's a very good criterion for us. Now, rewriting this under the form of a theorem that we will refer to as the integral test, we assume that we have a function f that is continuous, non-negative, and decreasing on the interval from 1 to infinity, and in that case the series of general term f of n converges if and only if the integral from 1 to infinity of the function f converges. When you apply this integral test, you will have to verify these assumptions that the function is continuous, non-negative, and decreasing on the interval you're considering. Now, one of the tools we used to reach this conclusion was these inequalities. And you see that if we assume that we're in the case where the series is convergent thanks to the integral test, in other words, the improper integral of f is converging, then when we pass to the limit as n goes to infinity in these inequalities, we obtain that the series is in between the integral of f from 1 to infinity and the integral of f plus the value of f at 1. So that gives us some way to estimate the sum. And we'll see in another video in this module that we can do better than that to estimate the sum. In fact, we can estimate it with whatever accuracy we want. Now let's look at an example on how we could apply this theorem. We want to know if the series from 1 to infinity of n over e to the n square is convergent. The first observation is that we can think of this series as series of f of n, where the function f is x e to the negative x square. Because of course when I divide by e to the n square, it's the same as multiplying by e to the negative n square. And this is clearly a positive and continuous function if we restrict ourselves to positive x. It is also decreasing, at least on the interval 1 infinity, because, and we can easily check that looking at the derivative. The derivative here, I have a product, so I can use the product rule. Get derivative of x is 1 times e to the negative x square. And then I have x times the derivative of e to the negative x square that I calculate with the chain rule. And I get negative 2x e to the negative x square. When multiplied by x, we get negative 2x square e to the negative x square. Factoring the e to the negative x squared, we get e to the negative x squared multiplied by 1 minus 2x squared. The exponential is always positive, and the parenthesis is clearly negative if x is at least 1. In fact, if x is at least the root of 1/2. So that means that the integral test applies, and that means that to decide the convergence of the series, we only need to decide the convergence of the integral. And we know how to calculate integrals. So I look at this improper integral from 1 to infinity of x e to the negative x squared. By definition, it is a limit as t goes to infinity of the definite integral from 1 to t of the same function. And we can calculate this definite integral from 1 to t by substitution, simply making the observation that if we take u equal x squared, then du is 2x dx, so what we have outside this x dx is 1/2 du, and so I get the limit of the integral of 1/2 integral of e to the negative u du, and we change the bounds because we made a substitution in a definite integral. When x is 1, u is 1, so I don't change the lower bound of integration. When x is t, u is t squared, so now the upper bound of integration becomes t squared. The function e to the negative u is continuous on the interval from 1 to t squared, so we can use the fundamental theorem of calculus to calculate the integral. Namely, all we need is an antiderivative, which we can take to be negative e to the negative u, which we evaluate from 1 to t squared. What we obtain is a value at t squared, which is negative e to the negative t squared, which I can write negative 1 over 2e to the t squared. And then the value at 1 is 1 over 2e. When we look at the limit, when t goes to infinity, e to the t squared goes to infinity, and therefore 1 over 2e to the t squared goes to 0, which means that our improper integral converges and takes a value 1 over 2e. As a conclusion, by the integral test, the series that we are looking at is convergent. And moreover, if we look at this rough estimate that we discussed, in this case f of 1, the function f was x over e to the x squared. When I plug 1, I get just 1 over e. And we've calculated the improper integral to be 1 over 2e, so our series is a value between 1 over 2e and 1 over e plus 1 over 2e, which is 3 over 2e. Now again, in a later video in this module, we're going to see that we can do better to estimate the sum. In fact, we'll be able to approximate the sum with whatever accuracy we want. But for now, we're going to turn to the next video and look in particular at a particular kind of series for which we can decide the convergence using the integral test, series that we will refer to as P-series and will be a reference kind of series for us.